coffee talk, and we don't seem to get much.
They have good beer there.
Pretty consistent every week.
We moved our department meeting from Friday to Wednesday, which like made Friday open, and so yeah, and it's a lot of it's to do with Quinn. Quinn and Travis have done a good job of scheduling and trying to.
This is just for the online people.
Okay.
But so the video will have your voice and not maybe all of our voices chattering in.
That makes sense.
So it does nothing for in this room, but now the video will at least be.
Can I just put it on my belt?
Yeah, wherever, and then this just clips on to wherever is most comfortable on your collar.
I see. Thank you.
It doesn't need to be too close.
Yeah, I mean like halfway down.
Okay.
Your shirt front typically is fine.
Okay.
It's a little narrow.
Does the laptop need to check? Is that?
No, I'm worried about the boost actually.
This.
Yeah, because it's 7%. I thought it said. Oh, you know, I don't even know about that laptop. I brought mine. Oh yeah, mine's under the laptop.
Yeah, I really enjoyed it. I saw that you had the iPad.
So I'm gonna try.
Yeah, I emailed her a couple.
We might have to like daisy chain these together a little bit. Just don't tell the fire marshal. This then. We can actually plug this in. And I think it was just get us up. It was not an actual extension cord sometimes.
Because I couldn't do the whole thing earlier. Get a lot of
questions.
actually
And that's fine, because that could be forever. This guy, is probably, actually, can you pull it around like this way?
I like the scarf. It looks nice and warm. It looks nice and warm.
This is, I think as far as I can comfortably.
Yes, so this
Hey, how's it going?
Do not call the fire marshal. I'm pretty sure the extension cord plugged into the extension cord is not.
So I did that just because.
Oh yeah, that's fine.
But so we are fine to go ahead. We normally
Yeah, I was just trying to be sure it was level-ish.
I did, yeah. It was perfect because we got done with our hour and 40-minute drive. I walked in the door and it was right there. It was right where I needed it to be.
Both online.
Is there, Quinn, is there any particular place I should be standing because of the video?
It has a pretty wide lens.
Excellent. Because I tend to walk.
They'll be able to hear you. So
That's what's most important. Okay, thank you.
all right. Good afternoon. Welcome to our first official colloquium of 2020. I should have queued up Barbara Walters. This is 2020, but I didn't. Today we're happy to have Dr. Thomas Cameron from Davidson College, and I'll introduce his talk a little bit more in a minute. But just as a reminder that so we will have we have a colloquium this week, next week, and the following week. Then after that, schedules are a little bit up in the air because we'll have candidates for the actuarial position coming in, but I'll send out more information once that's set. We will have at least one OCSA report and some other things. So I'll send out a firmer schedule once we have all that stuff sorted out with the search. But regardless of all that, we're very happy today to have Dr. Thomas Cameron, who again is from Davidson College. He did his PhD at University of Washington?
Washington State.
Oh, I got the wrong one, sorry. Washington State, and is now a visiting faculty member at Davidson. And he was kind enough, so he was originally scheduled to come back in fall 2018. When you all will remember, we lost some days due to a hurricane. And so that didn't work out, unfortunately. But we're glad that he gave us another chance, although we didn't give him much better weather. But anyway, he's going to talk to us today about the rankability of data.
Thanks, Quinn. Yeah, thanks for having me. It's really nice to be at Appalachian State. It's nice to see the turnout that you guys have on a Friday afternoon for a math talk. I'm sort of jealous of that. So I want to talk to you today about the rankability of data, and really what I want to do is just tell you a story about something that I've been thinking about for close to 2 years now. So I want to mention some of the people that I've been working with. So really this problem was first posed to me by Tim. He's my colleague at Davidson College, and really for him this problem was born in sports. He's really big in March Madness, as you probably know, and some years seem to be very predictable, and other years nobody knows, right? And so this is where this idea first started for him. For Amy, she's at the College of Charleston. For her, and myself too, the problem is really born in the linear ordering problem. And so just to give you a little bit of an idea about that, in the linear ordering problem, you're doing an optimization and you're working over some sort of feasible region. And if you have an optimal solution, oftentimes you have more than one. And so the question becomes, okay, well, if you have more than one optimal solution, which one is best? And so this idea was born in the linear ordering polytope for her. So really, we all kind of bring a different dimension to this work. Tim brings his sports, Amy brings this optimization, Heather brings graph theory, and myself, I bring linear algebra. That's what my training's in, okay? So the fundamental question that we're going to be talking about today is, how suitable is a data set for ranking? If I give you a data set, I'm sure we can all form a ranking of it, right? If it's a data set that has pairwise comparisons, we could probably form a ranking out of that data set, but how meaningful is our ranking, right? This question has been asked in different ways throughout history, and given the broad audience that I have here, I'm just going to kind of highlight a few of these, and maybe some of them will relate to you. For instance, Lewis Carroll had this voting method, and essentially what is he asking? He's asking, well, how many voter preferences do I need to change to have a true winner of this election? How rankable is this data set? Kemeny and Young asked essentially the same question. They're just interested in more than just one winner to the election. They're interested in a full ranking of their candidates from top all the way down, okay? Slater introduced the minimum feedback arc set. Now this is one of the most famous optimization problems in combinatorics, and it's essentially asking how many edge changes do you need to make to a graph so it's acyclic? How many changes do we need to make to this data so we don't have any contradictions? How rankable is this data set? Tim, actually not too long ago, looked at the sensitivity of rankings. And what he was looking at was really the tail of page rank, and he was looking at how sensitive it was to just slight perturbations in the data. But this is essentially, in essence, a very similar question, right? If your ranking is very sensitive to noise, then how suitable is it for ranking anyways? It turns out Google doesn't care about the tail anyways. They just care about the top, so they're not at all concerned. And really, the first like formal introduction in literature using the phrase rankability came out in 2019. Okay, and there they essentially introduced a discrete optimization problem for measuring rankability. Okay, now that discrete optimization problem is essentially a linear ordering problem, and that linear ordering problem in some form shows up in Dotchin's voting method, the Kamini method, and this measure of rankability, and they're all NP hard. What I'm going to talk to you today about is a polynomial time algorithm for measuring rankability. Okay? So I'd like to kind of motivate this idea with an example, and this example has been on the minds of people at Davidson this last year because we had like a 8-point drop in the college rankings in 1 year, which was kind of interesting. So of course, you know, academic affairs freaked out and purchased all the private data that you can get from US World News. Anyways, but they let us look at it, so that was kind of cool. So just for the sake of illustration, I'm just going to worry about 3 schools, okay? I'm going to talk about Williams, Amherst, and Swarthmore. And I'm not going to look at all features that they rank the colleges on. I'm just going to look at these 5. So selectivity, faculty resources, student-to-faculty ratio, graduate retention rate, and financial resources. This is all I'm going to worry about, okay? Just to simplify the problem. And what I want to do is I want to cast this problem as a linear ordering problem. So what I'm going to do is I'm going to model this data as a graph here. And I have the colleges, 1 Williams, 2 Amherst, 3 Swarthmore, okay? And then I'm weighting the edges of these graphs based on the number of features that college I outperforms college J in, okay? So for instance, Williams outperforms Swarthmore in all of these 5 categories, okay? And if they're tied, then I just give a half a point to each, okay? So this is my graph, okay? And what the linear ordering problem asks you to do is it asks you to find a spanning acyclic tournament subgraph that has maximum weight sum, okay? So this is the graph that we're working on. What we want to do is we want to find an acyclic tournament, okay? So here's an example of an acyclic tournament. It's a tournament because between every 2 paired nodes, you have an edge, and the edge only goes one way. It's acyclic because you have no cycles, okay? And this, in fact, is one that has a maximum weight sum. But so is that one. And so you can see that we have 2 solutions to this linear ordering problem, and they both indicate 2 optimal rankings of these colleges. One, as they were ranked, 1, 2, and 3, but the other, 1, 3, and 2. So, which one's right? If this is the only information you're going off of, I'm not sure it's easy to tell. Okay? So just to give you an idea of the spectrum of what we're looking at, I'm just going to make up some data, okay? So the data that we actually were working with was right here. This would be like the ideal situation, right? This would be the situation where college 1 is better than college 2 and 3 at everything. College 2 is better than college 3 at everything. And this would be the ideal situation. There would be no dispute in what this ranking would be. Here's something that's just not too far from that. This one actually has a unique optimal linear ordering solution, right? But this one, maybe you could argue that the ranking isn't perfect. Maybe you could argue that that one feature that college 2 outperforms college 1 is the only feature that you actually care about. Okay. You get down to here, that's clearly not very good. Everybody's tied. Or maybe it's great, you know, everybody's a winner, you know? And then this one is just like you didn't do any work at all. You didn't even collect any data. That's not good. What do you want me to do with that? Okay? So what I'm going to do is I'm just going to normalize these. And I'm going to do pairwise normalization. And essentially, the edges now will have weights that determine the percentage of features that they outperform each other in, okay? And so the reason I'm doing this is because maybe rather than 5 features, we want to consider 7 features, okay? And it allows us to be a little bit more robust and handle different linear ordering problems that have different objective functions, okay? So, let me say a little bit more about this. So this digraph right here, this is what we've decided is our ideal situation, okay? And I'm going to call that a perfect dominance graph. Essentially what it is it's an acyclic tournament graph that has weights that are all 1, okay? But for me and for this talk, this will be what's called a perfect dominance graph. Okay? So essentially what we want to do is we want to measure how far we are from perfect dominance. Okay? And we could cast this as a discrete optimization problem and literally measure how many edge changes we need to make. But then we're still in this NP hard category. What I'm going to show is that we can do this a different way. Okay? So the first tool that I'm going to need is the Laplacian. Okay, so I'm defining the Laplacian for a directed graph. If you've seen the Laplacian for the regular graph, there's a little bit of difference here. For instance, my Laplacian is not symmetric, so I lose a lot of really nice linear algebra theory, which is unfortunate. But nonetheless, we'll still be able to do quite a bit, actually. So the Laplacian has main diagonal entries that are basically the out degree of the vertices. So this is the out degree of vertex 1, that's the out degree of vertex 2, and that's the out degree of vertex 3. The off diagonal entries are just the negative weights. What is important to note is that the sum of each row is always 0. And this tells you that 0 is an eigenvalue of the Laplacian, and it has eigenvector, the all ones vector. It also tells you that the Laplacian is a singular matrix and so on and so forth, okay? But there's some other cool properties of the Laplacian. We already said 0 is an eigenvalue. Here's something that comes up in theory quite often. It can be put into what we call this Frobenius normal form. Essentially, you could reorder the vertices and put the Laplacian into this block upper triangular form. Okay, and that comes up in theory quite a bit. And what's really nice is each one of those main blocks is what we call an irreducible M matrix. And a lot of the results I'm going to show you today rely on M matrix theory. Okay, I'm not going to dive into the results that much and prove them. I just want to give you some flavor and to see what we're doing and to see what we can do with the results. So let's look at these strongly connected components. So here's a graph, okay? And it has 2 strongly connected components. There's one here, and there's one there, okay? You can see it's strongly connected because you can always go from any vertex to any other vertex, right? So you can go from vertex 1 to vertex 2 along that edge. You can go from vertex 1 to vertex 3 from there, and so on and so forth. So you can go from any pair of edges, right? And this is that so-called Frobenius normal form of the Laplacian. And you can see that I have these blocks along the main diagonal that are corresponding to these strongly connected components. So I have this block here that's corresponding to this strongly connected component, and I have this block here which is corresponding to that strongly connected component. The entries here really tell you about the connectivity between these 2 components. In this case, the 2 components are isolated, so there's no connectivity, and that's why we have all these zeros up here. In general, that's not always going to be the case. Okay? Now, actually forming the Frobenius normal form is not all that practical in practice, because you have to think about all of these permutation similarities. Okay? So that's a lot of work. But you start thinking about the eigenvalues of the Laplacian and you start seeing what's happening in the graph. For instance, the number of isolated strongly connected components of a graph is just equal to the number of zero eigenvalues of the Laplacian. So, as we noted, this graph has two isolated strongly connected components, and it has two zero eigenvalues. We can say more with eigenvalues. You can actually tell whether your graph is acyclic. So this is a result that we presented in a paper that's actually just recently been published with linear algebra and its applications. But it's an if and only if statement about when a digraph is acyclic. A digraph with positive weights is acyclic if and only if the spectrum of the Laplacian, the eigenvalues of the Laplacian, are equal to the out degrees of the vertices. And so you can do a quick check. You compute the eigenvalues, and you can tell whether or not your Laplacian or your graph is acyclic. In fact, in the proof of the result, you can actually see a little bit more. Let's just highlight this first, though. So you see we have the 2 there. That matches with that out degree. We have these 2 1s. Those are those 2 out degrees. We have those 2 zeros. Those are those 2 out degrees, right? Now, the number of eigenvalues that you have that do not match the out degree of your vertices is the minimum number of vertices that are involved in a cycle in the graph. So if you have one eigenvalue that does not match the out degree of a vertice, you have at least one vertex involved in a cycle. Okay? You'll see really nice examples of that as we move forward. Now, we're interested in this perfect dominance graph. So what we have is a characterization of that. So a graph with weights between 0 and 1 is a perfect dominance graph if and only if the eigenvalues of the Laplacian are equal to the out degree of the vertices, and the out degree of the vertices are equal to n minus 1, n minus 2, all the way down. And you can kind of see in both of these what is causing this to be a characterization of a perfect dominance graph. This piece here is just the acyclic part, right? The eigenvalues being equal to the out degrees. That's just the acyclic part. The fact that the out degrees have to take on a specific value, that is the dominance. This is essentially n minus 1 because you need a vertex that dominates all other vertices. You need one that points to everybody else. You need a second place. You need one that points to everybody else except for the first one. And that's where these conditions are coming from. It is important to note that the eigenvalues by themselves are not enough. So here is a graph on 3 vertices, and it has the eigenvalue structure that you would expect to see from a perfect dominance graph. The reason you know that this is not a perfect dominance graph is because the out degrees aren't right? And you can see we only have one eigenvalue that is matching the out degree of a vertex. We have 2 other eigenvalues that are not matching. That tells you that at least 2 vertices are involved in a cycle in the graph. And in fact, it's exactly 2 in this case. So you get a lot of information from these eigenvalues. And this is really the heart of our measure. We're going to basically approximate the work that you could do with discrete optimization and measuring exactly the number of edge changes that you would need to make in order to get a perfect dominance graph. And we're just going to approximate that by taking an eigenvalue distance instead. And so what we do is you give me some graph data, okay? I'm going to do that pairwise normalization. I'm going to measure the distance between the main diagonal entry of the Laplacian, which is what the out degree should be, and what they should be, n minus 1, n minus 2, so all the way down. And I'm going to measure the distance between the eigenvalues of the Laplacian and what they should be. And then there's quite a bit of theory actually that goes into this, but this is just a worst case scenario. That the worst that both of these distances can be is n minus 1. Okay? Sort of a rabbit hole that isn't worth going down for the talk, but there's probably a good number of reasonable choices to make here for how we're going to measure the distance between these two sets. And we chose the Hausdorff distance, and it works pretty well for us, okay? So let's go back to those variations of college rankings that we started this talk with. So again, we have that perfectly rankable, and it has a rankability measure of 1. Okay. We have a little bit less rankable, and the rankability measure goes down. It goes down again, and keeps going down, and then the empty graph, you get 0. Okay. The one thing that is interesting to note is intuitively I would have liked this graph to have a much lower rankability measure. Our measure, it actually has a lot to do with the Hausdorff distance that we're choosing. It tends to be okay as soon as you start removing information. That's when it really starts being reflected in the rankability measure. So anyways, if we had used like a matching distance instead of a Hausdorff distance, this would be much lower. Okay. But the matching distance is essentially minimizing overall permutations, and that, yeah, it's too much work. So now, I told you I'm a linear algebraist, technically a numerical linear algebraist by training. That's what I did my work on in my PhD. So when we first got this measure, I said, good, this is nice, but I want to know how stable this measure is. My main concern was, what if we're close to a perfect dominance graph? We're just a small permutation away. Is this going to drastically affect the rankability measure? And the first thing that is the obvious thing to do is to look at the conditioning of the eigenvalues. And one thing that's nice is that you know that the perfect dominance graph has simple eigenvalues. Okay? So if you can figure out what the left and right eigenvectors are associated with these simple eigenvalues, you can compute the condition number of these eigenvalues. It turns out that the left and right eigenvectors are actually really easy to come up with for the perfect dominance graph. And we use that to compute this condition number. And this is a wonderful condition number. I mean, it's not 1, it's not, unitary condition number, but it's really nice. And one of the things that's nice is that the I here is inside of the square root. So even if you start working with graphs that are really large, the conditioning of these eigenvalues do not grow very fast. Okay? So essentially what you can do is you can use this condition number to get a bound on what's going to happen to the Hausdorff distance, and it's a pretty sharp bound. Okay? And so what I'd like to do is just illustrate these two results with an example. So here I'm starting with a perfect dominance graph. And I'm just going to perturb it a little bit. And just to make this realistic, I'm not just going to do any old random permutation. I'm going to do a permutation that reflects what I'm doing with the data. So for instance, I started off, and let's think about colleges. This was college 1 perfectly dominating the other 2 schools. Now, the college 1 only dominates in 90% of the rankings, okay? And that's where these 10% are coming from, okay? And this is what happens to the eigenvalue structure. Not much. You move those edges by 0.1. Coincidentally, in this case, the spectrum moved by 0.1 as well. So that's a nice result. That's a really nice result. In fact, the out degrees actually moved more than the spectrum did in this case. So, what I want to do now is give you an idea of how these results are being used, okay? I very much came into the team with a theoretical goal in mind. I was like, we need to swap this NP hard work that we're doing with something else. And the reason is because our hope, our dream, our sights are set on big data sets. Our sights are set on big data sets from machine learning and learning to rank algorithms, and Tim's sight is set on March Madness. So eventually, we're going to work with big data. March Madness is really hard. I hope that something works, but I'm not completely optimistic about that. Anyways, so we start small, and these provide really good illustrative examples of what we're doing. So there's this Big East football conference. It doesn't exist anymore. It was in existence from like 1991 to 2012, and then just sort of got meshed in with other conferences afterwards. But what's nice about this conference is that the conference is small enough that it really is round robin in style. Every team played every other team exactly once, and that really doesn't happen. I don't know much about Appalachian State football, but I'm imagining that you don't play every team in your conference every year. I don't know if there's anybody who follows the Appalachian State football here. No? Yeah? Okay, excellent, excellent. Anyways, this provides a really nice natural setting to work on because it matches that problem that we developed really well, okay? So here's an example, okay? So this is 2001 for the Big East data, and I'm ordering the vertices based on their ordering as a result of an optimal linear ordering problem. And you can start seeing it's a little big, so at first it might be a little overwhelming, but you can, if you start looking specifically, just start with the best team, team number 1. It really does have a perfect dominance structure. Team number 1 beat everybody, lost no games. Team number 2 beat everybody except for team number 1. Team 8 lost to everyone. Team 7 lost to everyone, but they did beat Team 8. Team 6 lost to everyone else, but they did beat Team 7 and Team 8. So you can see it's almost perfect dominance. There's actually only one problem. Right there. That is the only problem. If you switch that edge, bam, you get a perfect dominance graph. I mean, it's kind of cool. We actually did find a perfect dominance graph. It was in the Mountain West Conference football, which was just surprising to everybody. Anyways, this is the only cycle involved in that entire tournament. And you can see that being reflected in the eigenvalues. You have a 0, that matches Team 8. You have a 1, that matches Team 7. You have a 3, that matches no one. 7 matches Team 1. 6 matches Team 2. So the only eigenvalues that don't have out degrees that match are the 2 complex eigenvalues and 3. That tells you that at least 3 teams are involved in a cycle, and in fact, in this case, it's exactly 3. Pretty cool. Here's another year. Without even looking at the graph, just looking at the eigenvalues, you know that this is very different. None of those eigenvalues match an out degree. They're either complex or 2.46 and 1.60. So you know that every single team is involved in a cycle. In fact, In 2001, there was only one cycle. There are 205 cycles in this graph. And not that the eigenvalue structure is necessarily picking this up, but there are cycles between really different teams, like 2, 5, and 1 has a cycle, right? So this seems right away like something that's probably not very rankable, okay? So here's all the years. I'm going to talk about ranking fit in just a moment, but here's all the years. And the rankability is that spectral rankability measure that we developed in this talk, okay? And you can see 2001, pretty good. 2007, not so good. Interestingly, it also picked up another year that seems to be very problematic, and that's 2004. And 2004 is really weird, because in 2004, 2 teams left the conference and only 1 team came and joined the conference. So they had this really weird shift in the structure of the conference. They, in fact, lost their 2 best teams. The best team in this conference was Miami, Florida. Okay, and they were dominating every single year. In fact, 2001, 2002, and I think 2003, they went undefeated. So they left the conference, and I think it was Virginia Tech or somebody else also left the conference, and it was Cincinnati or something that joined. And it makes sense that there would be a rather sharp dip in the rankability in those 2 years, because you're bringing in a lot of unknown by removing the 2 best teams and just adding this team that's never been in the conference before. Anyways, so I guess my main takeaway from this data at this point in time is I had no a priori knowledge about the Big East, and you're able to just run these measures and you go, oh, well, 0.86 looks pretty common. Wow, these seem like really big red flags. I bet you something interesting is happening there. And it turns out that there is. And so that's a nice, again, polynomial time algorithm for just saying these years don't quite match the norm. Now let me tell you a little bit about this ranking fit. So ideally, if you have a good ranking for your data, you would expect that it would represent the data well. And what we mean by that in this sports context is that if I gave you a ranking, you should be able to like go through the year and determine as many as possible outcomes with that ranking, okay? And so what we're doing with this ranking fit is we're giving you the percentage of games that were correctly calculated by the linear ordering optimal ranking, okay? And there is a very strong correlation, which is nice, to what the rankability is saying and what the ranking fit is saying. And again, the ranking fit requires NP hard work. You have to solve that linear ordering problem, and then you have, well, that's the hard work. And all the rankability is doing is computing an eigenvalue problem. And so we're essentially just giving you an a priori measure of how meaningful or how confident you should be in this linear ordering problem, okay? So I'm much more into chess, actually. So I decided to bring my own flavor to the group, and I started looking at chess tournaments. And chess tournaments are really nice because they're usually always round robin in style. And so there's this one tournament in particular that I've always been fascinated by. It's called the Cyclic Cup. And it interests me because, for one, it's had some pretty historical achievements in the Cyclic Cup. I'll talk about what I mean by that in a moment. But it's it's this invite-only tournament that has a very small number of players. The first edition of this tournament only had 4 players. Okay, and they were like Magnus Carlsen and just a few other just top-notch world chess champions. And it's not blitz style tournament, which means that they're given a decent amount of time to decide their moves. And when you have world chess champions with time, it's like sort of a snooze fest for some people because it's draw, 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 draw. Everybody just draws. I think the most recent chess tournament, it took till like the 6th round of the tournament for there to be an actual win. They might want to think about that, but that's not the point. So I'm going to model this tournament in a very similar way. So I'm going to model this by putting weights on this tournament graph that represent the number of points that a player I scores against player J. And the points are basically given by this. You get 1 point if you win, and you get a half a point if you draw. Okay? And some of these tournament editions were in fact double round robin, so it's completely possible for a player to get 2 points against another. Okay? And what I was really interested in when I did this study is I wanted to see how the data evolved as the tournament evolved. Okay? So what I'm doing is I'm doing like a round by round rankability analysis of every year of this tournament. And not surprisingly, the start of the tournament has very low rankability because nobody's played yet. And what's interesting is to see how the rankability increases as the rounds increase. Here's the first year. So the rankability just really grew, and just hit this optimal peak that was never really matched by any other year. And here's the most recent year, 2019, where, as I noted, there wasn't an actual outright winner until like round 5 or 6. And so you can see what seems to be normal for this data, at least for what we've collected so far, what's available. What seems to be normal is right around here. And what's weird is this, and what's really strange about this year is that it's the only year where the rankability took a dip towards the end. It's the only year where there seemed to be a conflict in the data towards the end of the tournament that didn't match what was happening at the beginning of the tournament. And actually, this year's the most interesting out of all of them. This year, what was his name? He's an Italian chess player, and I'm losing the name. It'll probably come to me. But he won the first 7 rounds outright. I mean, this was historical beyond historical. He came into a world chess style tournament and just won. First 7 rounds. He had draws his last 3 rounds. And this is what's happening in the data, is there's this clear dominance by this player, but the last 3 rounds don't resemble that. And so the rankability took a dip. That was really cool to see. Anyways, yeah, so yeah, that's kind of the idea, is we're using this polynomial time algorithm to get insight into how useful ranking problems are, and using that to get insight into what this data is telling us. Okay, just because I have some time, let me just talk a little bit. This is sort of off the cuff, but let me tell you about some of the things that we're doing right now. So I'm just going to go back. So this whole idea came into really characterizing this so-called perfect dominance graph, right? And we came up with this spectral degree characterization. Now, characterizations of directed graphs do not have a really great history. The spectral theory has been predominantly about regular graphs, non-directed graphs. And there's a very simple reason for that. Regular graphs have symmetric matrices associated with them. And so you get this wonderful theory coming out from the eigenvalues. The eigenvalues are always going to be real. The eigenvectors are going to be orthogonal. And there's a lot that you can do there with that. You lose that immediately here. Okay? And so the question really becomes is what is an appropriate way for characterizing digraphs? Is just using eigenvalues in general enough? And oftentimes it's not. We got lucky with this perfect dominance graph because the eigenvalues were simple. But that's not always going to be the case. Sometimes you'll have multiple eigenvalues. And unlike in the symmetric case, the multiple eigenvalues could be defective, meaning they have a higher algebraic multiplicity than they do geometric multiplicity. And so all of this plays a role into why characterizations of directed graphs have not been as successful. Okay? So this problem here spawned a brand new direction of research for us. And what we're doing right now is we're looking at how can we characterize digraphs? What tools are there in linear algebra that allow us to characterize digraphs? And one tool that we found that works incredibly well is the numerical range of a matrix. Does anyone familiar with the numerical range of a matrix? No? Do you mind if I put this up? I think I have about 5 minutes, so. Yeah, I can just turn this off.
Yeah, so there should be a button that says mute, maybe mute, oh no.
Oh, yeah. Just turn off or mute.
You can just turn the projector off.
Thank you. This is the numerical range of a matrix. It's a set of all quadratic forms of the matrix where the x's are normalized. Okay? And this set has been studied thoroughly. It's a wonderful set. It's a convex set, for instance. And it has lots of really, really nice properties, okay? And so what we've been doing is we've been looking at the numerical range of the Laplacian same condition, normalized x. The only other condition that we add is we add that the x has to be perpendicular to the all ones vector. And the reason is because the all ones vector is the eigenvector associated with the zero eigenvalue for the Laplacian. Okay? And so essentially what we're doing is we're trying to remove that zero eigenvalue from our consideration. All right? And there's a reason for this. So let's imagine that let's imagine that this is our numerical range, okay? This value, oh, well that's definitely not going to be what it looks like. There we go. It's going to be symmetric with respect to the real axis. This value right here at the leftmost real point is the algebraic connectivity of the directed graph. And so what we've been doing is we've just been studying the shape of the numerical range of the Laplacian. And we've already identified several classes of graphs, digraphs, that we can completely characterize by the restricted numerical range but can't be characterized by the eigenvalues of the Laplacian. So that rankability project has really just turned into a whole nother project on characterizing digraphs. So, all right, well that's where I'll end. Questions? Yeah.
When you were looking at the Big East conference, did you compare how your functions and everything you did to the data ranked the teams versus how the conference ranked the teams? Was it always the same?
It's very rarely the same. So the conference ranks the teams specifically on the number of games they win. And I don't exactly know the rules for how they decide tiebreakers. Does anyone know? So they don't, they may not, but they have some rules for how they're deciding ties, and we're not implementing those same rules in our linear ordering problem. And often what's happening is, there are multiple optimal rankings for the linear ordering, and so we're just picking the one that our Cyclic solver tells us, right? There are probably several others, multiple ones in some cases, that we could have chosen. And we're just choosing one and going through and doing the ranking fit based on that one. What's interesting to note, for the ranking fit, it actually doesn't matter which optimal ranking we choose, because the objective value is the same. And the objective value is essentially the number of games you're correctly going to predict. Yeah.
Is there any work done on, what happens if you don't need, a perfectly, what do you call it, a total ranking or something like that, where you're just classifying things according to, 5 slices or something like that, good, medium, bad, terrible, or something like that.
Mm-hmm.
Is it possible to do something using what you're talking about to do that kind of thing? And does that make the problem easier or more difficult or anything like that?
Just shooting from the hip, it sounds like it's going to make it more difficult, right? Because now you have possibly several gold standards or ideals that you're going to compare against. We ultimately, when we first were doing this, I just wanted to determine when the linear ordering problem had a unique solution. But that turned out to be very challenging in and of itself, and so we decided on this perfect dominance. It's a very extreme gold standard, right? Because not only is there a unique linear ordering, but there's absolutely 0 violations anywhere. And that makes it somewhat less realistic to work with in practice, but it made it easier to do some theory for it. Yeah?
So when you were showing kind of earlier on the sort of pairwise, normalized weights and everything.
Yeah.
So, right, the sort of dynamicist person in me wants to take that and just find a steady state and think about a random walk on that matrix, and so certainly that's a matrix with at least non-negative entries, so you have a greatest eigenvalue, which may or may not be simple. I guess if they're all positive, it's simple. But I mean, so does that? I guess my question is that dynamic sort of point of view, right? My sort of way from a dynamics background of thinking about this is to just think about, if let's say in the case of all positive entries, I do have a simple eigenvalue, which is 1. That eigenvector gives me sort of the steady state distribution, and so I can take and order now just the entries in the eigenvector.
Mm-hmm.
Why is that not the right way to do this? Because I'm sure it's not.
Well, what's the goal there? To get a ranking?
Yeah, to get a ranking.
Yeah, and that's sort of, I guess, where our interests diverge. We're not really interested in the ranking. We're more or less interested in how meaningful the ranking is. And essentially what we're doing, when you do the linear ordering problem, you're working over a polytope, right? And what we're really trying to do is find other ways of describing what the optimal face of that polytope is. How big is it? How many edges does it have? That's essentially what we're trying to do. What you're describing just sounds like another way of maybe thinking about ranking the problem.
So the question is more about kind of the space of rankings
Yeah.
and less about what the particular ranking is.
Yeah, yeah. That actually kind of brings up like a really natural thing that Tim is very interested in doing is like, are there years where all these different ranking methods are going to point to sort of the same conclusion? Are there years where they're just going to be all over the map? Does rankability tell you anything about that? Because there's always several ways to rank something. So, yeah.
When you found the perfect dominance graph, what did the eigenvalues look like?
So for the perfect dominance graph, the eigenvalues are this. Right? So like the example that we were working with was 1 dominates both 2 and 3, and 2 dominates 3, right? That's our perfect dominance graph that we were working with, and so the eigenvalues in that case would be 2, 1, and 0. And keep in mind, the eigenvalues themselves don't characterize that directed graph. You also need the out degrees. So the out degrees in this case are also 2, 1, and 0.
Questions for our speaker? All right, well, if not, let's thank our speaker one more time.
Thank you.